I'm Wilson, your MC for the day. Before we start, may I request that everyone put your handphone on the silent mode. Okay, thank you. For this morning, we are honored to have invited Mr. Amory Lovins, the co-founder, chairman, and chief scientist of the Rocky Mountain Institute from US. The RMI is a leading institute in energy efficient and a non-profit organization in the USA. The RMI shows a business how to create competitive advantage and increase profit by doing what they do far more efficiently. Mr. Lovins has advised industry in more than 50 countries for 4 decades and has experience in more than $30 billion worth of new and retrofit projects worldwide in 39 sectors. And this morning, Mr. Lovins will be sharing with us his presentation on advanced energy efficiency for data center. Mr. Lovins, please.
Well, thank you. Is there anyone here who was not in the buildings talk just now? Okay. So forgive me, please, if I repeat some of the same material, but this is really a much more specialized talk about data centers. And some of what I'll say might surprise you a little, so I started you off with a quote from Marshall McLuhan that only puny secrets need protection. Big discoveries are protected by public incredulity. In the data center business, if you compare, so let's say, the United States 2005 to 2000, you find that the amount of data center base we have installed has more than doubled, but the electricity use has grown more than that because the power per unit has been going up, mid-range and high-end. So total, there has been some increase in the energy intensity. And in many new U.S. data centers, the electricity costs more than the equipment, and most, even 3/4 of the equipment capex is not for the servers, not for the IT equipment, but for the cooling and power supply. There are many different numbers floating about on where the energy goes. Intel's nominal numbers, which of course vary widely, show that if you have a 100-watt IT load, typically your total input will be about 275 watts, which goes to various places. Actually, there's huge variation. Lawrence Berkeley National Laboratory has done excellent work understanding that. And you'll notice that the server load shown in blue is a widely varying fraction of the total electricity use in different facilities. The California Energy Commission and the New York State Energy Research and Development Administration have also done benchmarking, and they find, for example, that there's over a factor 2 difference between the best and worst HVAC facility or efficiency between different facilities. Now, in this case, if you compare, let's say, these two, which have such a huge difference in the HVAC energy, the bad one uses standard air-cooled cracks, no economizers, constant speed fan, and keeps everything on all the time, including a lot of humidification. The efficient one saves over half the HVAC energy with a central chilled water plant, airside economizers, variable frequency drives on the central AHUs, not much humidity control, and they monitor their data and respond accordingly. It's not that hard. Now, we did a design exercise with the data center and IT industries in San Jose just over 5 years ago and put out about a 100-page report, which you can get from our website. And it showed how to save about 89% of typical data center energy with lower capex, faster construction, better uptime, and much of it turned out to be retrofittable. we paid a lot of attention to hardware and not nearly enough attention in hindsight to the software and compilation. But we did get into super efficient cooling and power systems and how we could multiply load savings, as I'll describe, through integrative design. And we also looked at the real estate model, the need to charge by watts more than by square meters, because most of the costs are actually related to watts. Now, for a major client a few months ago, just to show how this work has advanced, we built on that work and found that without special IT hardware, all with what is now state of the shelf, and with quite conservative assumptions according to this firm's experience about virtualization, we could save over 80% of the energy without any material effort on software compilation or applying the accelerators, formerly called coprocessors, that now come in many varieties and are an extremely effective way to speed up computation without much energy. The expected CapEx saving is about 50% if we only buy the cooling equipment that's needed, or about 20% if we buy a lot that won't be needed anymore, because this system ends up with no chillers. We're not sure whether the engineers will be comfortable with that yet. But the loads in the temperate climate, this is not in Singapore, could all be handled passively according to standard mechanical practice. However, in a hot climate, you can do the same thing with desiccant cooling, as I'll describe. So you still wouldn't need refrigerative chillers. And there was a highly integrative design and a lot still to be done on the software side to push the savings to and above 90%. Now, I used to work for an inventor, Edwin Land, who was very good at rearranging one's metal furniture so that you'd stop having the old idea about how to do things. You've probably seen this problem in books on creative thinking. Find the solution that connects these 9 dots with just 4 lines without lifting the pen from the paper. Can you go 1, 2, 3, 4? No, now you go to 5. That's too much. You need 4 lines. Can you do it diagonally? 1, 2, that isn't going to work. And of course, you have to think outside the box to find the 4-line solution. But then it turned out there was a 3-line solution. If your paper's wide enough, you can always do this, not going through the center of the dots. And then other solutions started to come up from the students, 1-line solutions, the origami method, just fold up the paper, the geographic method with a very long line, the mechanical engineering method, take a tool called a scissors, cut out the dots. There was no rule against that. The statistical method, you keep stabbing the crumpled up paper over and over again with a pencil until you go through all 9 dots at the same moment. Or the 9-year-old girl who said, you didn't say it had to be a thin line, so I used a really thick line. If we look for the solution with 4 lines, we're not properly creative in finding other solutions with fewer than 4 lines. So we really have to let go of the old ideas to see new, radically simpler ways of doing things. I live in the Rockies, where it can go to minus 44 Celsius at 2,200 meters elevation. It's not a reliably sunny climate, and you can get frost any day. But in the middle of my house, I've harvested 28 banana crops with no heating system. I didn't need a heating system. It was cheaper up front to put in super insulation, super windows, air-to-air heat exchangers, and get rid of the heating system, saving 99% of the heating energy and $1,100 US of CapEx. Then I reinvested that plus some more money, $16 US a square meter net total, to save also 99% of the water heating, 90% of the household electricity, which would be $7 or $8 a month if I didn't make it with solar. Half the water, all a 10-month payback in 83. Here's a house comfortable at plus 46 with no air conditioning, although not with Singapore humidity. cheaper than normal to build in volume, saving about 90% of normal U.S. energy. Here's a house in Bangkok saving 90% of the aircon energy at no extra cost with better comfort. All these houses spanning the range of the Earth's climates show that integrative design, optimizing the house as a system, not the components by themselves, can often make big energy savings cheaper than small ones. Contrary to economic theory, this is much to the amusement of the economists, because they're used to thinking the more energy you save, the more and more rapidly the marginal cost of the next unit of savings goes up until it gets too expensive and you have to stop. Well, the insulation in my house acts this way, but it doesn't act that way for every component. In motors up to at least 220 kilowatts, there's actually no correlation between price and efficiency. I can get this very efficient motor cheaper up front than this very inefficient motor, and they also have more than a $20,000 present valued saving in OPEX if you go to the efficient one that's cheaper. So don't assume that efficient kit costs more. In God we trust, all others bring data. You have to shop for efficient kit, and then quite often you find that efficiency doesn't cost extra at the level of components, but it does for insulation. And yet, it would be quite wrong to insulate my house only to the level that will pay for itself from the saved heating fuel, because if I put in enough insulation, I get rid of the heating system. I no longer need furnace, ducts, fans, pipes, pumps, wires, controls, fuel supply arrangements. So I save 99% of my space heating energy at a lower cost than if I'd tried to save little or nothing. I'm getting expanding returns, not diminishing returns, to investments in energy efficiency. And why get there the long way round when I can tunnel through the cost barrier directly to that destination? Well, let's think about how we can do this for data centers. First, another industrial example. A runaround pumping loop for heat transfer in a factory was redesigned to save, according to the designer's measurement, 92%, although he'd expected 86% of the energy, with less cost, working better, with two changes in design mentality. And those who were here earlier this morning, please forgive my repeating this, but it actually bears repetition. It's such a nice example. The first of two changes that we learned from Mr. Liang Lok in the back here was to use big pipes and small pumps, not small pipes and big pumps, because the friction in the pipe goes down as almost the fifth power of diameter. But the engineering textbooks tell us to make the pipe only as fat as will repay its greater capex out of the saved OPEX over the years, the saved pumping energy. And this is methodologically wrong because it leaves out the capex of the pumping system. The pump, the motors, the inverters, the electricals all have to be big enough to overcome the friction. The friction goes down as nearly the fifth power of pipe diameter. Therefore, the size and roughly the cost of the pumping equipment will get smaller as almost the fifth power of pipe diameter. But the pipe gets costlier only as about the second power of its diameter. So clearly, optimizing the whole thing together, not just the pipe, we should use fat pipes, small pumps and motors, and total capex goes down. Then we should lay out the pipes first, then the equipment. Because if we lay out the equipment first in the usual way and then tell the pipe fitters to run their pipes all the way across the room around all the obstacles, friction will be 3 to 6 times what it should have been if it had gone straight and short. The pipe fitters, of course, like the present arrangements, they mark up the extra pipes and fittings. You pay them by the hour. They don't pay for your bigger pumping equipment or your bigger electric bill. But for you as owner, it's better to have fat, short, straight pipes than thin, long, crooked pipes. So then we got about a 86 to 92% saving in pumping energy, less capex, and a 70% saving in heat loss with a 2-month payback because it's easier to insulate short, straight pipes. We also left out other important benefits that had we fully captured them, would probably have saved another factor 4 and lowered the cost even further. So we're talking not about just equipment. Just like in cooking, we don't just talk about ingredients. We need a recipe. We need a chef putting the right things together in the right way to get a really tasty result. And I'll emphasize pumping systems as the biggest use of motors. Fans are the second biggest. They have the same physics. And together they use half of motor energy. Motors use most of the world's and Singapore's electricity. A big motor running in continuous duty uses its capex worth of electricity every few weeks. And there are 35 things you can do to a motor system to save about half its energy between the meter and the input shaft of the machine you're driving. It's very cheap because if you do the right 7 things first, you get another 28 improvements as free byproducts. But before we fix the motor system, let's go further downstream. What I mean by that is if I feed 100 units of fuel into the classical power plant, only 1/10 of that energy comes out the other end as flow. But then the compounding losses can be turned around backwards into compounding savings going from right to left. So if I save a unit of flow or friction in the pipe, I'll save 10 units of fuel cost and pollution, climate change back at the power plant, and my capital equipment will get smaller, simpler, and cheaper. If I save 1 unit of flow or friction in the pipe, I can save 2.5 units of sizing and roughly capex in the motor. Now, where do our loads come from in a data center? What do we have to cool? Well, if we start all the way downstream to minimize, for example, the amount of air or water we need to move around for cooling, then we would ask, where's the heating coming from? And yes, you really can fry an egg on a modern processor. It takes about 11 minutes at just 1.5 gigahertz. It's apparently very good with brown sauce. This was a British guy that showed this. But let's go back a bit. Let's see, 92. So that's 16 years ago. I had a small hand in the design of the first really energy-efficient desktop computer. It was the first one to use an LCD display. It had PCM-CIA architecture. It was the first pizza box form factor. And with much argument, they were persuaded at IBM to use a very efficient power supply. Normally they use these absolutely dreadful switching power supplies that might be 60 or 70% efficient at full load, but they get dreadful at part load, which is where they spend most of their time. And instead we found a mid-90s% efficient Swedish one the size of a pack of cigarettes that gave terrific power quality and had quite flat efficiency across the load curve. It cost an extra $1.30 or something like that, so the bean counters didn't like it. But then I pointed out that it didn't need a fan, so that would save a lot of money. And then they could market the ergonomics of silence, and it wasn't drawing air in through the computer from the absent fan, so you wouldn't get dust depositing on the chips and inhibiting heat transfer, and therefore causing more failures and more warranty costs. So it turned out this was a very good deal once you looked at the side benefits. And also, because there was no fan, you could lock the whole thing in your desk drawer for better security. It made the case much smaller because you didn't have this big box from the terrible power supply, and it was more resistant to EMI. So that turned out to be quite a good deal. Now, in our own operation, we made a simple server substitution to further illustrate the point. We replaced several Windows servers with a small Linux box the size of a paperback book, made in Canada, running nominally 14 watts. That's the peak, though. It normally pokes along at just a few watts. It has no fan. And it's faster and more capable than the boxes it replaces. And its total cost, including software, is less than that of just the NT license fee on the boxes we replaced. So the economics were really easy. But it saved 98 or 99% of the energy and a lot of space. Now, this same thinking, of course, applies to servers. for data centers. 6 years back or so, a 1U rack-mounted Wintel solution would look rather like this and have these attributes. Notice the 160-watt power supply, and notice the 9 fans using around 30% and in some cases 40% of the total server energy to take heat that shouldn't be there off the motherboard and move it into the room so you can do stupid things with it. Now, Chris Hipp, who invented the RLX blade server, did the same thing this way with under 16 watts at the same time, taking the power supply off the motherboard to a very efficient power supply feeding the backplane and using a very efficient chip, at that time the Transmeta Crusoe, running very long instruction words. And you could fit 72 of these blade servers in 9U. Well, Dr. Fung at Los Alamos National Laboratory then built, and here's Chris Hipp, a 160 peak gigaflop supercomputer by putting 240 of those blade servers into a single rack. And later they raised it to 240 peak gigaflops. So this was 8 times denser and 5 to 8 times less power intensive than the Wintel solution. And in an uncooled 31 Celsius hallway at about 2,500 meters elevation where the air is thinner, so it's not so good for cooling, this had perfect uptime. And it ended up using 7 or 8 times less energy in a typical iterative science application than the Wintel solution, and it had a 3 or 4 times lower total cost of ownership. You paid more for the hardware because at the time blade servers were not very common. They were made in much lower volume, so they cost more, not less. Obviously in high volume they cost less because there's less to them. And yet you paid an order of magnitude less for power supply, cooling, space occupied, downtime, and sysadmin. So you ended up 3 or 4 times cheaper for the whole thing to own and run. And compare this to the Q supercomputer at the same lab with its giant cooling towers. Now, to be sure, that's the Ferrari, and this is the Camry. This is not the fastest computer in the world, and this is one of the fastest. And yet, the tortoise can beat the hare. If the mean time between failures is shorter than the computation time, as it can easily be for the Q computer and the kinds of things they do with it, then that one rack Green Destiny Dr. Fung did will beat the Q computer, and just as the Camry will beat the Formula One over a long drive, because the Formula One brakes a lot. And actually, it turns out the mean time between failures is set not in general by hardware, but in data centers it's set as to maybe 90% by software bugs and human error in setup and operation. So we need to think very carefully about making our hardware extremely fast rather than our hardware and software simple and reliable. It may be the wrong direction. Also, remember that typically equipment life gets cut in half for every 10 Celsius hotter it runs. It's basic physical chemistry. So, for example, at 1.6 volt, a Pentium 3M versus the Transmeta running a bit faster has a factor 2 difference in Celsius temperature. That's a 60 times difference in the hardware-based mean time between failures in round numbers. Very interesting. We really pay for running chips hot. Now, there are interesting examples from a few years ago of using this efficient approach in supercomputers. Here's a desktop version, 14 gigaflops for 170 watts. Or that's the Orion. Or here's a under your desk one, 300 gigaflops, 2,000 to 37 pounds mass. The price goes down by a factor 10 or 20, and you go from 13 kilowatts to 0.3 kilowatts. Now, back in 2003, when we did this exercise with industry, the way we thought about a a kind of efficient hyperserver, was a 6-watt CPU, very long instruction word, low power, optimized workload, 3-watt hard drive, we can probably do a bit better now, and well cached, and 5 watts for everything else, energy optimized. Just a 6-watt power supply, rack-based, and a 3-watt DC to DC converter on board. 1 watt of fluid cooling out of the backplane. Total 21 watts, and that would compare very nicely with the standard 128-watt one-use server, but we'd also save half from better resource allocation. Well, that was 2003. Now we can do considerably better than that. And you might ask yourself, why do we have so many problems in data centers from cramming so much equipment and so much heat release into so little space? Well, because we really adopted an immature real estate model that made the watts look free to the tenants. And of course, Ken Brill has estimated even 5 years ago that a Tier 2 data center would cost you about $12,000 a kilowatt, but 4/5 of the capex was for the kilowatts, only 1/5 was for the space, the things that occupied space. In a Tier 4 facility with full 2N redundancy, $22,000 a kilowatt, 3/4 of the cost driven by the watts, not the space. But if we reward tenants for conserving square meters, not for conserving watts, then as operators we're stuck with a lot of extra costs that we're not charging for. This is crazy. It's completely misaligned incentives. And this is really as much a cultural as a technical issue, but fortunately the operators who misaligned their costs with their fee structures are starting to go out of business, and some of the smartest operators are now charging mainly by the watt, not by the square meter, or much less by the square meter, so that costs and fees get properly aligned, and this turns out to be very good for both parties. Then they don't try to get such impossible to cool power densities. Now, how do we get heat out? Traditionally, we use air. Air has about 3,500 times less heat moving capacity than water per liter, and also air takes an order of magnitude more energy to move for the same heat flux than water does. Water can be more precisely delivered and controlled and heat exchanged than air. And there's really no problem in good engineering mixing electricity and water. There are a lot of industries that have been doing it safely for many decades, even though it's not conventional. So we're starting to see now either direct conduction or heat piping of heat to the backplane, and then liquid cooling from there. In fact, Raytheon has a nice system of subambient cooling. They put water under a vacuum, so they can get COP over 40 on the heat transfer and extremely high power densities. They do this routinely for certain military systems. If you use, by the way, a dielectric liquid that's not water, you could even use a transverse electric field across the heat exchanger to make microturbulence that greatly increases the heat transfer density. Or you could, of course, instead of liquid cooling from the backplane, heat pipe directly up out of the backplane right through the roof to coolers up on the roof, which can be radiant. Of course, the key is to make the equipment efficient in the first place so that you don't have so much heat to take away. Again, start downstream. Well, one good way to get rid of heat is to stop worshiping the dead. Either embalm or bury dead servers. We have these zombie servers that arise and walk in the night. They're on, but they're not doing anything. We should put the hottest and most heat-tolerant and the least mission-critical units at the top of mixed racks. Why is it that failure rates are 3 times higher at the top than at the bottom of the rack? It's because heat rises. And yet we often just put things in randomly without this sort of prioritization. We should make sure that all the power management features are enabled. That's good for typically 20% or greater savings. We should make our vendors do it by default. And if we temporarily disable those features, we need to put them back. Many people assume very stringent criteria for both dry bulb temperature and relative humidity in data centers. Where do the numbers come from? Well, they don't come from the equipment manufacturers. If you go back to the original specs, you find they're often much more tolerant of those wide operating conditions than the operators assume. In fact, we had a case many years ago with a Shell data center whereby mil-speccing the equipment at a modest extra cost, we were able to get enormous environmental ranges to be permitted, and we saved a lot of money up front by taking mechanicals out because we didn't need such stringent operating conditions. We often have very tight RH control when we don't need it, and quite often you find it's fine to use a much broader range of RH and then make sure that you have calibrated sensors so you know what you've really got, because the sensors tend to drift. It makes sense to control ventilation by real-time CO2. Often there won't be people in the space and you don't actually need ventilation. You only need cooling, if that. Outside air economizers are good for an 81% saving in Northern California data centers. Much less here, but still interesting at times of year. Chilled water cracks, it's very straightforward to put in variable frequency drives and turn off what you're not using. And of course, very fundamental, implement thoroughly and carefully hot and cold aisles with air seals. The concept is quite simple. Traditionally, you just have alternating hot and cold aisles, but the trouble is that unless you have an air barrier here or up above, they get mixed up. You'll get hot air spilling over into the cold aisle and so on. But using the kind of linear flow thinking that we have in clean rooms, you can even retrofit this kind of thing in an existing open plan data center. And when Rumsey did this in Northern California tests, either of these options would save 3/4 of the fan energy and get better uptime. Now back to this diagram for a minute. Let's think about once you've reduced the flow through the pipe or the duct, how can we reduce the friction? Often you see a pair of pumps that are either helping each other or one's an in-place spare for the other. And they're drawn and built like this, so all the time the flow goes through 2 right-angle bends and usually 2 valves rather than no bends and no valves or 1 valve. But when Peter Rumsey retrofitted this strange-looking Y-joint and sweet bend and diagonally through the air piping arrangement on a condenser water pumping loop, he saved 3/4 of the pumping energy and eliminated 15 pumps that will never again waste electricity and maintenance. Negapumps are the best kind. The old chilled water in this case, pumping power was here. The new chilled water pumping power on variable speed was down here. Notice the scale goes all the way to 0. Quite dramatic. And instead of laying out our pipes this way from the cooling tower to a central chiller, how about that way? Everything gets better. Big pipes, small pumps, untangle the layout, get rid of most of the plumbing. Now let's apply this same diagram of reasoning from downstream to upstream to a data center. Normally the operator will just look at the electricity coming in at this point. But actually we have to remember there's grid loss and power plant loss upstream of that. And mostly we only look at the power used by the IT loads. But because of low utilization, only a small part of that actually is working. And it's not just low utilization, it's that we often use servers designed in such a strange way that at, let's say, 1/4 of their computing load, they'll still use 2/3 of their energy. They don't turn down properly. They don't turn off the bits that you're not using, or they don't clock down properly. And then, how about computation we're doing that doesn't add customer value, but is caused by bad code? You see, in a typical data center, looking at this whole diagram, just about 1% of the power plant fuel or less ends up producing computing cycles that are needed and wanted. So imagine the upstream leverage of starting all the way downstream here and writing terse code, like we used to do in the days when 16K was a lot of RAM. I'm not sure many people here are old enough to remember that, but my first computer, I'm 60 years old, was an IBM 1620 serial number 3 running on paper tape. And the people in the Hackers Conference who wrote most of the fundamental building blocks of today's IT system wrote extremely terse, elegant code. We hardly do that anymore, quite the contrary. But if you really start here and get systematic, you can ultimately leverage 2 order of magnitude fuel savings at much lower capex. How do you do it? Well, you wring out unwanted computing cycles. You make your IT equipment about a factor 4 more efficient. Then you make your cooling and power overhead about an order of magnitude lower. I'll talk about that in a minute. And then you do on-site polygeneration to cut out about half the power plant losses, so that instead of, say, a 50 or 60% efficient combined cycle, you'd have a 90-odd% efficient trigen rig. The logic's pretty clear. How do we do it? The biggest untapped potential, and we still know the least about it, is at the level of system architecture, operating system, compilation, and application software. We do know that virtualization, combining the functionality of many separate physical servers into a single server, commonly condenses the number of servers you need by manyfold. Factor 5, 10, 20 is not unusual. I think the highest I've heard of so far is 78, because we're so used to having one server for one application and for one operating system. But now the virtualization software is quite good at combining them. And of course, we should be selective about our storage so that dead data that we hardly ever need to get at should go to the slower units that use less energy. Thin clients match the capability to the task. And then, of course, I keep getting back to bloatware. Does anyone actually have data on how many comp cycles you need to run the same task under different operating systems? I ask because a friend of mine went to buy one of those beautifully thin little Sony laptops, and he asked the knowledgeable dealer, how long will the battery run? And he was told it'll run 6 to 11 hours under XP or 2 to 5 hours under Vista. I wonder what it would do under Linux. Obviously, Vista is doing a lot of stuff whose value you may or may not attach much importance to, but it uses a whole lot of energy. And I'm afraid that in the data center environment, we have a lot of really bad software. How well does your operating system allocate watts and other scarce resources? You know, it's probably worth something upwards of $40 present value to save a watt in a data center. Does your operating system put that value on the watts and allocate system resources accordingly? I kind of doubt it. Okay, now let's go upstream into the power supply in the IT equipment. The average of all the servers that Lawrence Berkeley National Laboratory measured a few years ago, and it takes special equipment to measure it properly, is like this, that maybe at 2/3 or so output, it's a little over 70% efficient. Notice what happens at low load where it spends a lot of the time. It just goes all to hell. Now, sorry, this should say uninterruptible power supplies. A little continuous improvement here. For uninterruptible power supplies, the single or double conversion machines typically are down in this range. Flywheel systems can get up in the upper 90s. Now, why on earth would you not specify at least 80+%? In other words, the best of these, or better still, this one. And why would you specify this one instead of these? one of the major power supply makers in Taiwan has a chairman who's interested in this stuff, and he's pledged to me that he's going to start putting on the nameplate of every power supply the load versus efficiency graph for that unit, and challenge his competitors to do the same thing, because he thinks he makes better ones. Watch for them. A very big issue is AC versus DC power supply. There was some Swiss work showing roughly factor 2 savings with DC bus in telco applications compared with similar internet apps running on an AC bus. In this exercise in OT 3, we found that the real difference was culturally, not technically driven. Basically, most IT people had no telco experience and didn't realize that telcos for decades and decades had been running happily on 48 volts DC, so they didn't realize it was possible. Lawrence Berkeley National Lab found savings probably upwards of 20% from DC supply architecture. Intel, with a different sort of study, 400 volts DC, found 7% of total electricity for the facility, 6% of total capex, half the downtime, and a third of the space could be saved with DC. To my mind, the most convincing data are coming from NTT Facilities, a very large Japanese operator, builds most of the data centers in Japan, and it's historically a telco firm. So they have enormous experience of this stuff. Of course, one other architecture that comes to mind is, why not have a distributed uninterruptible power supply, have a bunch of local low-voltage DC batteries, just like you're running a bunch of laptops. Not a completely crazy idea. But here's what NTT found. Look at the DC 48 volt efficiency as a function of power output versus the AC 100 volt efficiency. Look at the system load factor. Look at the air volume, much less needed for DC than for AC. And these are the kinds of reductions they're getting by going to DC. It obviously depends on the equipment and the duty. And now the real stunner, look at the unavailability. Over an order of magnitude improvement for DC versus AC uninterruptible power supply. A case closed as far as I'm concerned, because the economics are great. And what you pay so much for in a data center is uptime. This is reflecting field data for 10,000 uninterruptible power supplies and 23,000 DC systems. They've never had a failure in a DC system. I think that's pretty convincing. And in fact, using a variety of devices, they have an experimental center now where they've gone 100% DC, about 1,200 amps at 48 volts, saving half the space and a fifth of the electricity. They even use DC for the fans and the lighting, not just for the IT. No AC need apply. Now, Mr. Lianglock talks about using all the parts, eating the feet, great attention to detail. And I think I shan't trouble you with this example I gave earlier from lighting. But in cooling, remember we need to expand the range of conditions in which we feel comfortable, minimize unwanted heat gains, cool passively where possible, cool actively but non-refrigeratively where needed. And then we can get into super efficient refrigerative cooling, but we don't actually need it because we can do the whole job just with handling the latent load with desiccant or absorption, and then hybridizing with evaporative to get over 100 units of cooling per unit of electricity. Here's how super efficient cooling can work in Singapore, again with Mr. Lee's standard practice. COP around 6, actually 0.58 nowadays for comfort. Or if you do dual chilled water temperature, one coil specialized for condensing, the other for sensible load, you can get that up to COP 6.8. about 0.52 total kilowatt per ton for a process cooling application. And with low face velocity coils, as I described in the previous talk, so we move the air slowly and the coolant quickly. It takes much less energy to move coolant than to move air. We use a shallow, sparse coil instead of a deep, dense coil, and we run the face velocity down under a meter per second so as to preserve the extra surface area of the droplets that form on the fins. We get better dehumidification with the 20th the airside pressure drop. Now, how would we go about cooling a data center? Here are some ways to think about that. Reducing the heat load, of course, takes no energy to achieve and generally reduces CapEx, as we saw with the Green Destiny machine at Los Alamos. An airside economizer uses pretty close to no electricity and has a tiny marginal cost. It does need proper controls and especially maintenance. A waterside economizer, strainer cycle on the cooling tower. Remember, you can run a cooling tower here at 0.010 kilowatt per ton. Will be down in that range, or if it's not quite as good, maybe a little more, and it'll cost about $100 US per ton. A heat-based system will run somewhere in the same range, maybe a little more, and you can run it off the waste heat of a trigen system. It's dearer. It's up to maybe $2,000 US a ton with absorption, or considerably less with a desiccant-based, desiccant plus direct indirect evap cycle, and very low OPEX. The water-cooled central chiller system might run, depending on climate, 0.4 to 0.8. Around here, roughly 0.6 kilowatt per ton, down approaching 0.5. And it might cost $1.5 or $2,000 US a ton. But what do we all do? We buy air-cooled cracks, 1.4 if you're lucky kilowatts per ton. And it looks cheaper, but not from a whole system perspective, and certainly not in OPEX. Let's do a little deeper dive into how we would get COPs upwards of 100. Of course, if you start with one of Mr. Lee's terrific COP 6+ systems, water-cooled centrifugal, you could boost that further by just putting a little desiccant on it to handle more latent load. It would cost what water systems cost. And actually, even if your chiller only ran a third of the hours and you only paid 8 US cents a kilowatt hour, its electricity cost would still match its CapEx. So is there a cheaper way to handle sensible and latent load even in a tough climate like this? Well, I'll give you a couple of examples. We recently had a high-tech factory where we were able to eliminate all 22,000 tons of chillers. It was in a temperate climate, hot in the summer, cold in the winter. And it turned out, by going carefully through the psychrometric charts, we could get 70% of the annual ton hours for free from airside and waterside economizers. And the COP was 352 for the cooling tower and about 125 for the system, because you have to count the chilled water pump. Still not bad. Well, the other 30% of the ton hours in this case, mainly for summer condensing, we were able to get by creating what we called Mount Sherbet. We would go out at night with a fire hose about 5 cold nights a year. It did get cold in this place, below, say, -2°C, and we'd simply spray a mountain of slush in some unused land they had out back, and that was COP probably hundreds. So it was over 10 times as efficient as a chiller, and it would cost a lot less. And a hectare, 15 or 20 meters high of slush would yield about 17 million ton hours of zero-C meltwater through the rest of the year. Of course, the engineers were rather startled by this because they're used to chillers, so we started asking things like, well, tell me, in your engineering judgment, what part of this is unreliable? Is it the freezing? Is it the melting? Is it the pumping? Now, in Singapore, you won't do this. What could you do? In a hot climate or without land, at your land prices, obviously, that's a big deal. Well, a Pennington cycle, or a more efficient version even called a Fensil cycle, puts in a desiccant to create a hot bone-dry air into which you then evaporate a little water to make the air cool and a bit moist. And then you can mix that with outside air that's been cooled in a sensible air-to-air heat exchanger, so you get the desired mix of dry bulb and wet bulb in your exit conditions. And Train's Type 3 alumina adsorbent CDQ desiccant actually can regen at 30 C. We used to have to go to about 55 C for the old Yazaki and Hitachi desiccants, but now you could probably regen right off the exhaust air of the data center at 30. And with very efficient air handling, this should achieve COP at least 100. Oh, by the way, we can use another trick called a passive latent heat exchanger. Here's how it works. Take your 100% outside air building, and as the air comes in, pre-chill it. I'll tell you how in a minute. Take the condensate that drops out of it, run it preferably by gravity to where you're exhausting air from the building, evaporate it into the exhaust air, thereby evaporatively cooling the exhaust air more or less to wet bulb ambient, capture the sensible cool with a heat exchanger, and bring that sensible cool back passively in a heat pipe to where you started, and that's how you pre-chill the outside air. In other words, you recover the dryness that you paid to create in the air you're exhausting, and the only moving part is the working fluid. Now, you could, of course, go to a trigeneration system with an advanced engine or microturbine or a fuel cell. And then you have medium to high temperature waste heat. So you could, for example, stack it with absorption on top. You could use a Kawasaki over 1.6 COP triple effect on top of the cycle, then a desiccant under that. Or you could run all desiccant. And, of course, if you have a number of fuel cells that are cross-bust and moderately redundant, you can eliminate your uninterruptible power supply and its costs and losses. Oh, by the way, just basic physics works. One of our Hewlett-Packard experts notes that with liquid cooling, just having the device cold plate below 75 C, which is a typical rating, can be achieved with a simple passive radiator, especially with a properly selective surface. So how low can we go? Let's look at how many kilowatts of auxiliary power, that is for cooling, air handling, and power supply, we need for each kilowatt of IT equipment. The Uptime Institute said that when you add up all the overheads, the best you can do is about a 60% overhead on top of the IT use. Lawrence Berkeley National Lab thought they could get to 19%. Our report in 2003 said 13%. And early this year, we showed roughly 8 to 11 was plausible, and Lawrence Berkeley now agrees with that. How would you do it? Well, you'd cut your electric upstream supply overhead down to 2% by using amorphous iron transformer and fatter wire. Copper's cheaper than kilowatt hours. And then you would use a very efficient direct current bus floating on batteries or on a flow battery. Then your chilled water production, you would use an enthalpy-controlled airside economizer, the 0.010 kilowatt per ton cooling towers for water-side economizer, and a desiccant-driven cycle in your climate. Now, for all the air handling and humidity control and lighting, you can use super efficient equipment and mechanicals, an extended RH range, chilled water cooling, and very efficient lights with good controls. In fact, you don't need any lights when there's nobody in the building. The servers don't need light. And actually, maybe we can now envisage getting even below this, down to a 5 to 7% overhead. That's where our latest designs are driving to. Watch this space. I don't think we'll get it lower than 0, but we can get close. So if I think about this with beginner's mind, I go back to a famous old book on how to write well by Strunk and White. It's called The Elements of Style. And it used to have in the old edition Rule 13, which said, omit needless words. And it went on to say, vigorous writing is concise. A sentence should contain no needless words, and a paragraph no needless sentences, for the same reason that a machine should contain no needless parts, and a drawing no needless lines. This doesn't require that the writer omit all detail and treat the subject in outline, but that every word tell. So if I apply that philosophy to engineering a data center, and we start all the way downstream, first we'll omit needless cycles, computations that yield no customer value. We will have terse code well compiled. We will then omit needless boxes by virtualization, by using dynamic infrastructure and provisioning, so we turn things on and off according to what we need at the time. We will efficiently allocate all resources and turn off whatever we're not actually using. Why is it that our data centers have a constant load while the workload on them, the IT load, varies by at least a factor 3? There's something wrong with this picture. We then emit needless watts. We buy negawatts. We use little cooling or all liquid cooling or radiant cooling. We don't use power supplies at the server level. We do everything on DC bus. We probably don't need fans. We then emit needless infrastructure, especially things on the critical construction path that would slow us down. And just think about it. If we have direct heat pipes from the backplane, they can run right up through the roof and radiate up there. No fans, no chillers, no raised floor. You can add, if you want, wet condensers if you're in a dryish climate. You could add a rooftop desiccant booster. You could add a sunshade over the radiators and make it photovoltaic for your most critical loads. And if you want to, you can use complementary air and water side economizers with computational fluid dynamics designed for passive cooling. Or maybe you can engineer the entire building to be a radiator. You're paying for structure. Maybe you can have an extra function of rejecting heat. And let's not forget the real estate model. As an operator, we need to make sure we're getting paid not for square meters, not for watts, not for boxes, not for cycles, but for customer value created. That means rethinking a lot of the business model and what is it we're selling. So think again about this and that 2 orders of magnitude prize by starting downstream and compounding all the savings all the way back to the power plant and to the CapEx budget. I hope that's enough to start a useful conversation. Thank you.